I like to add power on indicators to my projects, particularly mains powered ones, just for two reasons. It helps diagnostics, and it's a safety feature because when you see it lit, you know the unit is powered. Although you should never assume that an indicator is actually working at any point. You should always double check it, particularly if you're coming up to a piece of equipment that you've not been working on before. So traditionally in the fairground light controller type equipment, I used to put a neon indicator and resistor on the main side, and then an LED and resistor on the low voltage side. And it meant that when you went up to the controller and opened the lid, if both LEDs were lit, then it showed that you had a healthy low voltage supply and a mains supply. But if the LED was off and the neon was on, it suggested that there was a problem with the power supply. It was just a very basic diagnostic aid. And likewise, I put a lot of self-diagnostics in my controllers, so the triac circuits would have the neon on the main side and the LED on the sort of opto-isolator side, and it was just a very simple arrangement. The neon and the resistor was across the triac, so that when the triac was off, the neon was on and vice versa. And that meant that the LED on the indicator board and the neon would just alternate backwards and forwards with the pattern. That just made diagnostics very easy. So it's always useful adding these indicators in. And if you've got a low voltage supply, then that's easy, because all you need to do is basically stick an LED and resistor in and bingo, you've got your indicator. Dead easy. However, if you've just got mains voltage, the easiest thing is to use a neon. That would be what's traditionally used. It might not be terribly panel friendly in modern equipment, but it's very functional. So let's stick this neon and a resistor across these terminals, and these are going to be live at 240 volts. At the moment, although the unit's powered up, you can see the classic neon indicator in here shimmering away. Not shimmering to the naked eye is the iPads introducing the shimmer again, but even though that's lit, it means there's power to this unit, but it's not going to power up until I close these pins down in the lid into these receptacles. It's just a safety feature of the quick test. So let's grab the soldering iron and some solder and solder this neon on. Now, I can't put the neon indicator lamp directly across the mains, because if I did, it would try and pass as much current as it could, just like LEDs would do. So it needs to have a resistor put in series. So I've soldered that lead, and here's the resistor I'm going to use, in this case, a 220k resistor. Now you can get neon indicators, panel indicators, that have already got a resistor built into them, but I actually recommend, even with those ones, adding an extra resistor, because quite often the manufacturers of the neon indicators use the smallest lamp they can get and overdrive it, and that not just puts huge stress on the lamp goes black quite quickly, but it also stresses the neon, and the neon can fail, not the neon, it stresses the resistor, and the resistor can fail too. So here's the arrangement. I've got a neon plus a 220k resistor. Now, if you do use one of the ones that's pre-terminated, you can add another resistor in series. You could add, say for instance, a 220k resistor, a 100k resistor, depending on your mains voltage, and it will reduce the brightness of the actual indicator. And it's maybe an inconvenience that it's not going to be so bright, but it will last a huge length of time. And if you guys have seen the early videos that I've done of the Mountain Breeze ionizer repairs, a lot of the problems with the Mountain Breeze ionizers was the resistor failing on the neon and neon indicator on the front panel, because the resistor would slowly burn and then it would flash over and then it would take out tracks in the circuit board. It was just a very silly design thing. So let's close this down. We've got a 220k resistor in the series of the neon, and the neon is now lit. It's not super bright. I'm going to shield this, but I'm not going to poke that live wire. And I will say that when you underrun neon indicators, they shimmer a little bit. The light tends to just flow backwards and forwards up the little electrodes. I quite like that effect. I like the sort of shimmering effect. It depends on the actual type of neon, what current you're running it at, and also just the age. As it gets older, it tends to do that more. So that's the simplest approach, a neon and resistor. Now, doing the computations for that, this is on 240 volts. The neon will typically have a running voltage of about 50 volts. Let's say 40 volts. So just to make a nice round figure. So to get the resistor power dissipation and so on, let's divide, let's say I equals V over R. So that's 200 volts, because that's a 240 volts minus the neon voltage, divided by, and the value of the resistor, which in this case is 220,000 ohms, equals just under 1 milliamp, times the 200 volts being dropped across the resistor equals 180 milliwatts, so it's well within the rating of that resistor. And also, because the neon itself drops a bit of voltage, these resistors only rated for about 250 volts DC, but that drops about 50 volts, so it brings it, I wouldn't say it brings it perfectly within the 250 volts sort of DC limit, but it does bring it much close to the rating of these resistors, so it makes it very simple. You just tend to have a quarter watt resistor. So that's the simplest indicator. But you know, it would be nice being able to use an LED, and this is where I'm going to have to bring the notepad in. Casually makes sure that I've turned the power off before I start desoldering things. I have stuck my soldering iron onto live connections before. It's violent, and particularly when you're concentrating on a solder joint, it's quite dramatic. It leaves visual dots in your eyes for a while. So here's the notepad. Here's live, here's neutral, and let's base it on 240 volts, or 230 volts if we're being European compliant. So let's draw bus bars along and show all the different possibilities. Now the simplest thing we could do, and this is done a lot by the Chinese manufacturers, the real low budget ones, this is a little charging lead for a sort of rechargeable hot water bottle thing. And it's got the LED in it, and all it's got is a resistor. So let's start off with the first one. It's a resistor in series with an LED across the mains. Now, unlike the neon, the LED in this case is only dropping about 2 volts, because you have to be careful what type of LED you use. You have to choose one of the older gallium arsenide type technology LEDs. And it's not a recommended approach, really. Because the peak inverse voltage of these LEDs is usually rated about 5 volts, and that's the maximum voltage they can withstand in reverse, and that's going to happen in every half wave. So in keeping with the standard sort of style of the Chinese cheapo manufacturers, let's choose a 220k resistor, and let's do the maths for that. So this time it's going to be 240 volts minus, well, it's probably actually over 240 volts, minus the 2 volts. There's so little difference, let's just assume it's 240 volts. So 240 volts divided by 220k equals, so it's going to be 1 milliamp again, but times the full 240 volts equals, and it is actually slightly exceeding the quarter watt rating of this resistor. Also, the resistor will have its voltage rating exceeded, but these are minor technicalities. One of the ways to get around that, they grossly overload the resistors in this unit, for instance, but it's only lit while the unit's heating up, so they basically apply a diversity factor that's not going to be powered all that time. So let's make this arrangement up, and we'll see how it looks. The first decision you have to make is the type of LED you're going to use, because it's going to be running at very low current. And I'll show you a couple of different types of LEDs here. This is a modern high output one. So let's plug that into the 10 milliamp range here. And this is an old-fashioned indicator LED. So let's plug that into 10 milliamps too. We're not going to actually give them 10 milliamps, but this will make it more visible. So they're both lit, but it might not actually look like both lit. One looks so dim, and it really is visually dim, because although the same current is passing through it, it is a much lower efficiency LED. It is just an indicator LED. And the same happens with the green, but worse so. This is a gallium phosphide LED, I believe, and this is a gallium nitride LED, the modern one. And the comparison is even worse with the gallium nitride, because gallium nitride is so efficient. This one is a blazing bluey green, and this one's a soft apple green but very, very dim. And you'd think then that you want to use the brighter LEDs, but unfortunately, in the case of the gallium nitride, these ones are very easily damaged by the reverse voltage, so you're going to have to use gallium phosphide, or preferably just the traditional red gallium arsenide. But we'll use the brighter one of the red ones. So let's get a resistor, and it doesn't matter which way around this goes, because even though it is polarity conscious, because it's polarity sensitive, it doesn't really matter, because ultimately it's going to see both sides of the waveform. So let's splot some solder on this. Grip it by something that's not going to be thermally conductive so I don't burn my fingers. So any random lead, and we'll solder that onto there. And we'll get another 220k resistor. I could get the original 220k resistor. Let's get the original 220k resistor. And let's solder that to there. And I shall wet both these leads with solder and then flow them together. A bit of a rough and ready joint, but that's fine. So this LED will be passing 1 milliamp, and it will flicker quite strongly. Let's show that. You can see it flickering quite strongly because it is only lit for half the wave, and that resistor will be dissipating its full power, because ultimately this LED is only lighting in one direction, but it's still, when its reverse voltage is exceeded, it will be lighting in the other direction. It will be passing current, should I say, in the other direction too, but without lighting. If you're using a gallium nitride LED, then you'd have to provide protection for the reverse voltage. And the way you could do that is simply by adding a diode, an ordinary diode, in reverse across that, so it clipped that reverse voltage. You could even add 2 LEDs in inverse parallel, but that would be the simplest fix. So the next thing we could improve efficiency is by making this actually half wave. So if we then have that resistor, the 200, well, this time we can actually use a lower value resistor and put a diode in series, and then the LED, then the diode will use a 1N4007, a 1 amp diode, but just, you know, it's a generic diode. And we'll put this in series with another LED, or in fact we'll put it in series with this LED, but because it's only going to be seeing half the power now, because it's only going to be on for half the cycle, we can use a lower value of resistor. So we'll probably use a 120k resistor. I've got a 120k resistor here. So I shall just solder that up right now, and then we'll try it out and see how it looks. So let's get the 120k resistor. I'm just double checking I'm putting the right one in, because one of the other experiments involves a 1k resistor, and that would be quite visually bright from the LED perspective, and the resistor would emit smoke immediately. It might go pop. Much as you want to do that. You know, at the end of the video I will put an LED right across the mains, just to show you what happens if you do. I warn you in advance though, it's not usually terribly exciting, but then, famous last words, it might actually turn out exciting in this instance. Now I have to observe which polarity the LED is, because if I get the polarity wrong here, the LED won't light at all. The LED, that's the positive lead. I think that's positive lead. We'll find out when we do this. So let's solder the diode in there and to there. Those leads are getting very hot right now. Yeah, those leads are getting too hot to hold before the resistors actually, the solder's actually cooled down. So let's hold it a wee bit further away. Meanwhile, the solder dries out, all the flux is off the solder, so it's going a bit sort of crusty and dry. Right, let's try that. Let's get the notepad out of the way, so there's a better contrast. And this should be running the LED at twice the current, but it'll still be lighting half wave. So it's brighter now, but it is still visibly flickering, because it is only lit on half the waveform. But that has reduced the dissipation across that resistor. Now you'd think at this point in time that you could then, because you've got a diode in series, you could then use the gallium nitride LED, because it's got reverse polarity protection, but in reality these diodes will let a small reverse current leak through, and you still need a diode across the gallium nitride LED to protect it against that. So what's the next variation in the circuit? The next variation in the circuit is to use a full bridge rectifier. And the full bridge rectifier, I would have to use the 220k resistor again. So in that case I used 120k there. These are just random values, just chosen. You'd have to actually, depending on your mains voltage, you'd have to calculate it. And I wouldn't even recommend using these values on 240 volts. I'd suggest using a slightly higher value just to reduce the dissipation. So actually, let's move that along a bit. Let's go back to 220k, but this time I'm going to actually use a bridge rectifier. So the classic bridge rectifier based on 4 diodes. And all the diodes point towards the positive terminal. So let's make this one the positive and this the negative. So the diodes always point towards the positive terminal. And a bridge rectifier is basically like a sort of like a series of one-way valves, if you will. So all the diodes pointing away from the negative towards positive, and I'm going to put the LED across from the positive, like that, to the negative. And what this means is that when the current's flowing in this direction, it's going to go through this diode, it's going to get blocked by this one, so it's going to go through the LED and then through this diode into the other leg. And when the polarity is reversed, it will then go through this diode, through the LED and through that diode, and of course the current's being limited by the resistor. So this time, because it's impossible to get this sort of reverse polarity as such, I'm going to use this actual bridge rectifier with a blue gallium nitride LED across it. And this is an actual implementation of what I've just drawn. All the bands are pointing towards the positive end. I'm just going to check I have connected the positive LED. Yes, I have. And all the bands are pointing away from the negative end. And the other 2 connections that each have a band and a non-band, they're the AC terminals. So let's get a 220k resistor and we'll solder it onto this and then we'll bang it on the mains and see how it looks. So double check, red, red, yellow, 220k, solder, so I'll remove that little arrangement. We'll put the resistor down here. This all starts getting complicated. You suddenly realise that actually the neon is so much easier in the long run because you don't have to worry about the rectifiers and things like that. But the upside of using this approach is that you can then choose the colour of the LED, and you know you're a bit more limited with the neons. You do get blue neons, but they tend to be very short-lived. They don't have a very good life expectancy compared to the traditional orange neon indicators. The phos, they tend to blacken inside. Should have actually put a bit more solder on this, but I think that's okay. So let's see how this looks. And this time I've got the advantage that it's a gallium nitride LED, so it's going to be visually brighter at a similar current. And it's not bad actually, it looks quite nice. You're probably not seeing that lovely shade of blue. I'm just being careful not to touch connections here. But yeah, that looks pretty good actually. That's starting to get quite usable on a panel. But again, I would choose either a higher value resistor or a couple of resistors in series to spread the voltage and also lower the dissipation. Now, if you really want to go for high output though, then we have to come to the capacitive dropper. And this can be quite a simple circuit because it is just an indicator. So for the capacitive dropper, we're going to use the bridge rectifier again, but this time we're going to put a capacitor in series, then a resistor, and this time the resistor is going to have a low value. It's only going to be 1000 ohms, so that's going to be 1000 ohms. The capacitor is just going to be a basic 100 nanofarad. It doesn't have to be that high a value. It's not a super high intensity situation. And that could be an X2 capacitor, or in this case I'm just going to use a generic 400 volt one. The X2 has the advantage it's really designed for use in mains applications. It is a safer capacitor to use, but these ones seem to be pretty reliable. And then that will then go to the bridge rectifier, which I won't draw in full this time just to save time, but I will just draw, it's basically that. Normally you'd also put a resistor across the capacitor to discharge, but if this is actually in a panel with transformers and things and it's across the power rails, it's not so critical. It's going to discharge through the rest of the circuitry. So let's do that. I shall desolder that resistor. Let's get some fresh solder in that too, so it's got a bit more flux. Let's put it in both. The resistor, the 1000 ohm resistor, its job this time is purely to limit inrush current, because when you first connect this capacitor, depending on when you connect it to the mains, could be at the peak of the sine wave, and it could suddenly charge the capacitor up. And the way this circuit works, on each half wave of the mains, a small portion of charge is going to get coupled between the plates of the capacitor, and a sort of almost like a push-pull arrangement. It's going to either, first of all, it's going to go through the LED, through the bridge rectifier in one direction and charge up the capacitor, and then when the polarity changes, it will discharge, and it will then push that current effectively back through the opposite direction and make the LED light up. That's sort of simplified description of what happens. I have plans to do a more complex video on electron theory, which will actually make you realise what electricity is, but that's definitely going to be a 2-beer video. That is going to have to involve lots of beer and whiskey and vodka and coffee and things like that. But will be a complete revelation when I actually get round to doing it. It's quite a spectacularly complex video, but I'm going to try and make it as simple to understand as possible, and once you understand, it just makes things like capacitors, resistors, inductors, suddenly everything will make sense. Now I've said that, I really have to get round to doing it, which is probably a good thing. That's going to give me the incentive to do so. So here's the 1K resistor going in to limit the inrush current, because as that capacitor charges up, it could be quite high pulse of current. The resistor, the 1K resistor, its function is to limit that to a maximum value. And if you consider that it's going to see potentially 240 volt across that 1K resistor, that would be about 1/4 of an amp, but it's only going to be a brief spike, so it's not going to see it on an ongoing basis, and it just takes the risk of damage, or reduces the risk of damage to the LEDs. The main advantage of this circuit with the capacitor is that the capacitor limits the current reactively. It doesn't heat up like a resistor would, which means that you're going to get a much brighter LED. That is now at the level that, I could point at a surface and it will illuminate it, he said, completely failing to illuminate the surface very well because it is white. But that is very bright now. So that just leaves one experiment. So this would be probably the best one if you wanted a modest intensity. How bright is that going to be? How bright is that? I can measure that. I've got a 1K resistor. What's the best way to do this? That resistor will see an AC. I could theoretically measure the current through that circuit by selecting AC volts and measuring the voltage drop across that resistor. Which is about 7 volts across a 1K resistor, suggests about 7 milliamps. That's not bad. That explains why the LED is so generously bright. And that just leaves one experiment. What happens when you put an LED directly across the mains without any current limiting whatsoever? And we kind of know what's going to happen. But I will warn you in advance, I've done this several times in the past and was always kind of disappointed by the results. So let's use this original red LED. And let's just tack it on like that. And this is not a recommended technique as an indicator, because the LED will pass as much current as possible. And I have to say, in the past, to give you an idea of what's like to happen, I'm going to point that sideways, because usually it just splits the LED in half. It doesn't always take the fuse out. But let's see what happens. Ready? That was rubbish, wasn't it? You hardly saw anything at all. What actually happened in there, it failed in a controlled manner. There was a brief glimmer inside. It's gone black inside. The little tiny gold bond wire has blown like a fuse, and because it was surrounded, it's just controlled the fault, and it didn't even go pop. So, but it's dead now. That LED is a dead. It's a dark emitting diode. So there you go. That's all the different sort of ways you can run an indicator on the mains, but by far the easiest of the lot, the one that I've not drawn in here, is just the 220k resistor, or whatever suits your local supply, and the neon bulb with its little electrodes inside. And if you underrun these neon lamps, they just last forever. You know, they really do last a very long time. And they also, at very low currents, they also develop that nice sort of almost like a little mini flicker flame lamp. But it's all, I would like to say, you know, it'd be great to be able to actually do that deliberately and have them just jittering about like the neon flicker flame lamp. But you can get 100 of them, and you can put them on a circuit board, and I've done that. With high value resistors, and some will do it and some won't. It's very unpredictable. But there you go, mains indicators.